recording. All right, so now we're going to go over the presentation I put together on the 2945 assembly improvements. We have here a photo of the assembly. The focus was these two stud components here. The old process, we used to put those in one at a time. They would line the part, cycle it, insert one stud, pick it up, realign it, cycle again, insert the next stud. We ran several time studies on this, examining each step that went into building this assembly. Tried to identify all of our bottlenecks, where our opportunities were for improvements. So you can see here, this is a layout of the E2 line. The E2 press cycles every 7.7 seconds. The first assembly here, putting in the single air fitting, was cycling at about 6.1 seconds. The second assembly here, putting in both studs, cycling at about 8.1 seconds. And the ringer here is cycling at about 7.7 seconds. So our initial time study that we did, we identified the bottleneck here at the second assembly and the ringer station. As you can see, the second assembly is cycling about 0.4 of a second slower than what our press cycle time is at. So that causes a backup on the line. The second assembler is constantly getting backed up into the first assembler. The first assembler has to stop, let the second assembler back up before they continue. The ringer was not much better off. They were running about exactly the press's cycle time. So anytime they would have to stop, put labels on the crates or anything like that, they were getting behind. The second assembly was unable to help them out even because they were already backed up. So our second time study that we did, we inserted the assembly fixture that would drive in both studs simultaneously in one stroke. Just by doing this, we gained a little over 0.6 of a second on our stud application. Where we were running at 8.1 seconds, now we're under 7.5. So we're underneath the press's cycle time at 7.7 seconds. We're able to flow a little better, but any mishap, they had to stop and get another box of components or whatever it may be. They're getting backed up. They're not quite fast enough yet to catch up. So the ringer did a little bit better here. We're by helping out the second assembly, increasing their cycle time, we were able to help out the ringer some whenever they would get backed up. So this helped out the ringer station just by inserting this assembly fixture a little bit. Our next time study, we reshifted rebalanced the line's responsibility. So where the second assembly was putting in both studs on the initial trial, now we moved the second assembly's responsibilities up to the first assembly, and the first assembly is down to the second assembly. So now we're driving in both studs on the first assembly. By doing that, by just rebalancing it like that, we gained another 0.5 second from our previous trial. So now we're under 7 seconds on our stud application, 0.7 of a second faster than what the press cycles at. The second assembly put in the air fitting, they're having no problem. The ringer is able to get help when needed from the second assembly, just because their application is so much simpler than where it was with the stud application. Our next time trial, we installed a curved backstop behind the assembly fixture. This helps line up the part, gives the plate less movement. Just by doing this, we gain nearly 2 seconds. So where we were at 8.1 seconds per stud application, we're now down to nearly 5 seconds, which is over 2 seconds faster than the pressing cycle time. We went to a larger diameter stud ring to help out the ringer. We identified that the ring that was going on the studs previously was a lot tighter inner diameter, a lot tighter, lot more difficult application. So we went to a larger inner diameter ring to help out with the application, make for an easier application. This got the ringer cycle time down under 3 seconds at 2 3/4 seconds. So now, looking at this, you have a good healthy flow. Each station is slightly faster than the previous. If we go to this one, this shows the initial time trial, putting in each stud one at a time, versus our last time trial that we did using the assembly fixture, driving in both studs simultaneously. Also, the arrows indicate the shift of responsibilities of the line. We took the stud application that was here at the second assembly, moved it to the first assembly, air fitting from first assembly to second assembly. So you see here, we gained 3 seconds, over 3 seconds on our stud application. We gained a little over a second on our air fitting application, nearly 5 seconds on our ring application. How that equates into or compares to previous years. In 2018, we averaged 3,416 pieces assembled over a 12-hour shift. After the improvements, the last 2 trials that we ran, we assembled 4,300 pieces, and on July 17th, nearly 4,500 pieces. That gives us a gain of over 900 pieces per shift. And equating that to a dollar amount of cost savings at $249 per hour total burden for equipment, labor hours, all that stuff. Previous process, 2018, we were producing each part at nearly 88 cents per part. After the improvements made to the process, the last 2 trials that we ran, we were producing at just under 70 cents per part. So that's a savings of nearly 18 cents per part. In 2018, we produced over 300,000. We produced 330,000 units. It's probably our highest volume assembly that we do out here in the metals department. So at 18 cents savings per part over 330,000, there's a potential cost savings of nearly $60,000 per year annually. But we, a lot of studying went into this. We, a lot of man hours. We had there was a team together that we had that did several time studies to identify all bottlenecks, all opportunities. I feel like we made some great improvements on this. Look forward to 2019 potential savings, and if we can continue this across the board on other assemblies, we see a huge benefit in all of our bonuses and profit shares and all that stuff. Anybody have any questions? All right, thank you guys.